We are going to continue to talk about electrochemistry, introducing electrochemical cells. There are two types of electrochemical cells. An electrochemical cell is a device where either I use a spontaneous oxidation or reduction reaction to produce electricity, so basically it's a battery, or conversely, I could apply a current from an external source to make a reaction that is not spontaneous happen anyway. So for example, when I want to make an electroplating of something. So these two types of cells have two different names. So electrochemical cells refers to any type, so it's the general term, and it divided into two categories. The spontaneous one, the one that you can use to make a battery, are called voltaic or galvanic. So they take the name, those two words are used interchangeably like synonyms. So you can shift, you can even sometimes see in the same book that they are going back and forth between the two. So they both takes the name from the two major scientists who develop electricity, so Volta and Galvani. The ones that are non-spontaneous are called electrolytic. So the word is a bit similar, there is a certain similarity between electrolytic and electrochemical. So it's kind of easy to make a confusion between the two, but electrolytic are the non-spontaneous one. Electrochemical means all types. So the difference is in the spontaneity and in the direction in which the electrical energy is going. For voltaic and galvanic, electrical energy is given off by the system, so you can use it to make a work, to have some useful work. In electrolytical, you have to provide the energy to the system by connecting the device to a plug in the wall or a generator. Let's take as an example the reaction we've seen multiple times and we also have performed in the lab. Zinc, solid zinc and copper ions. So if we put a certain amount of metallic zinc into a solution of copper ions, we would see a spontaneous reaction that consists into the oxidation of zinc. Zinc becomes zinc ions, losing 2 electrons. Those 2 electrons are acquired by copper that from an ionic form becomes solid. So as we said, if we can design a device that forces the electrons to go through a wire, we could take advantage of the spontaneous reaction, so that chemical energy, to transform it into electrical energy and light up a light bulb that we could connect into the circuit, right? So let's examine the different part of this voltaic cell. So this is a voltaic cells. It can also be called galvanic cells, and it's where the spontaneous reaction would happen. So we can produce energy. The system is giving off energy to the surrounding for us to use it. So you have the cell is the whole thing, but it can be divided into two halves. The semicell where the oxidation happens and the semicells where the reduction happens. Where the oxidation happens, we have the anode. So this electrode is called the anode. Where the reduction happens, we have the cathode. This is always true. It's one of the few things in life you can count on. How do you remember which one is which? Anode and oxidation all start with a vowel, while cathode and reduction both start with a consonant. Another way to remember it is an ox and a red cat. And we will go over this mnemonic again. The electrons are generated at the anode because that's where the oxidation of the zinc happens. So this bar of zinc is getting thinner and thinner as the reaction proceeds, because zinc will detach and become zinc ions. So you will have the zinc ions in the solution. The electrons, so this bar will be rich in electrons, that's why it has a negative sign. So in the voltaic cell, the anode is negative. Unfortunately, this is not always the case. as we will see in electrolytical cells, the sign switches. So, but in this case, it's a voltaic cell, the anode is going to be negative because the oxidation is happening here and I have a lot of electrons. The electrons are running through the wire, attracted by the positive side of the circuit, that's the cathode. So here the cathode is positive. In doing so, they can be used to do some electrical work. So energy is coming out of the system. The current flow is always opposite to the electron flows for historical reason. When they discovered current, they knew nothing about electrons. So they assumed that whatever was moving was positive. And then we figured out that it was electron moving and those are negative. So there is an incongruence for historical reason. It's too late to change things, basically. As the reaction proceeds, you will see that the electrode, the cathode, is getting bigger and bigger because more and more copper from the solution that initially is blue, as the copper ions acquires electron and become solid, they're going to deposit on top of this electron. So this electron is increasing in mass, while the zinc electron is decreasing in mass. Because these two electrons are part of the reaction, like the zinc bar is in fact a reagent and the copper bar is in fact a product, we call them active electrodes, and they change mass. One is getting slimmer, one is getting chubbier. As the reaction proceeds, you will have an accumulation of zinc ions on this side. Because they're colorless, that's not going to have any dramatic visual consequence. On this side, you will see the disappearance of copper ions. You may detect that because they are blue, so the blue will fade away. The consequence is an accumulation of charges. So here the solution is getting more and more positive, while this solution is getting more and more negative. This would create an obstacle to the flux of electrons. The electrons are moving from here to here because this is negative and this is positive. If the solution is becoming positive, it will, let's say, try to hold back the electrons, while here, if the solution is getting negative, is going to repulse the electrons. So this would eventually stop the reaction to happen. There has to be an electrical continuity for the circuit to work. The circuit needs to be closed, so there has to be a complete path for the electrons. The continuity is allowed through this. There is a connection, is the equivalent of a salt bridge. It's not a bridge, it's basically a physical connection, a tube that connects the two beakers, and you see this small thing in the middle represent in perspective a circle. That's a porous set. So it's a set that keeps the solution separated, otherwise if they mix there would be like a short circuit. But at the same time, through the pores, it allows certain small ions to move back and forth, allowing this, and this flux of ions back and forth, it's driven by the accumulation of the zinc here. So because here you are going to accumulate zinc ions, these zinc ions are going to attract negative spectator ions, for example nitrate, that can go through the sept. On this side, due to the disappearance of copper ions, you're going to have an accumulation of negative charges. So potassium ions that are in here can move through the sept and are attracted by the negativity of the solution, and they move there to keep it neutral. Why potassium and nitrate? Because those are spectator ions. They don't participate into the reaction, so they are sort of inert ions. It can be potassium, it can be sodium, it can be nitrate, it can be sulfate. It doesn't matter, as long as they can go through the porous disc or through the gelatin that fills the salt bridge. If we would change the pairing, so if, for example, we pair up solid copper with silver ions, then what happens is that the direction of the electrons changes. They are going to go from copper to silver. So it's the silver that's going to be reduced and is going to be the cathode. And the copper now is oxidized and is going to be the anode. So the oxidation still happens at the anode. What changes is copper. Copper is strong enough to take away electrons from zinc, but when it's facing silver, it loses the confrontation and is going to lose electrons. So the fact that the species is reduced or oxidized is not an absolute characteristic of the species. It depends on the pairing in the reaction. It depends what's confronting it. It's a bit the same as water behaving like an acid or a base, depending if it's in the presence of a base or an acid. So let's say that we have once again our voltaic cells built with zinc and copper, and instead of inserting a light bulb in the circuit, we insert a voltmeter. That is an instrument that allows us to measure the difference of potential between zinc and copper. So that would be the driving force that's pushing the electrons from one side to the other. The higher is that value, the stronger is the tendency of the electrons to move from one side to the other, the higher is the amount of work that we can extract from that battery. And if the reaction is in fact spontaneous, so if we have a voltaic cells, that value is going to be positive. So we could measure that the voltage for the zinc and copper pair is going to be 1.104 volt. So if we operate in standard condition, we call that standard cell potential, and it's indicated with the symbol E0 cell. So these little degree symbols implies that we are in standard condition, and cell is the potential of the overall cell. That would be the whole device that we are using. So let's just remember what is the standard condition. So, well, the volts are joules per coulomb, as we have said in a former slide. The standard state, it means that everything that's dissolved in water should be 1 molar. That is a pretty high concentration. If there is any species that's a gas, the pressure should be 1 atmosphere. If we don't have that degree sign, then it would be we are not in standard condition, and we would have to make some adjustment because of that. So that could be typically either because the concentration is not 1 molar. As I said, that's a pretty high concentration, so most of the time the concentration is lower than that, or it could be that maybe the temperature is not 25 Celsius. The problem is if I change the pair, if instead of zinc I have magnesium, I get a totally different value. I get 2.71 volt, so it's much higher. So that means that you know, when I pair up copper and magnesium, their behavior is more different. Their ability is more different than there is a higher difference between the two than there is between zinc and copper. So it makes it even easier for the copper to take away electrons from the magnesium. If instead I pair it up with lead, between lead and copper seems to be more similar, so the potential that I get is smaller because copper is still it attracts electrons, so its ability to be reduced is still higher than the one for lead, but it's not that much higher, right? So I really don't have a way to measure with just one number, just the ability of copper to be reduced, because there is no way I can build an alpha cell and measure it, because it's like I have only half of the circuit. I cannot have a reduction separated by an oxidation. So I cannot measure the ability of copper to be reduced on itself without pairing it up with something else that's getting oxidized. But then, depending on what is getting oxidized, I get totally different numbers. So I need an arbitrary baseline. It's a bit similar to the situation where we were trying to measure the delta H of formation of substances, and we didn't have a baseline, so we decided arbitrarily to assign 0 to use as a baseline the delta H of formation of elements. or when you measure the elevation of a location, you measure it respect to the sea level, but that's an arbitrary choice. The true elevation would be the distance of that point from the center of the Earth, but we can measure that. So we take an arbitrary decision, and as long as we all agree, it's going to be just fine. So in this case, what are we going to take as a baseline? We are going to take as 0, we assign 0 to the value of a hydrogen electrode, where you have the reaction of reduction, where H plus is gaining 1 electron, 2 atoms of H plus are gaining 2 electrons, and then connecting with a covalent bond and forming H2 gas. So obviously, because it's a gas, the design of the device is a little bit more complicated because you need to keep the pressure to 1 atmosphere and so forth. But then all you have to do is pair up this electrode with every other electrode and measure the difference of potential, and that's the value that we can assign to each alpha reduction. So by using this little subterfuge, we can build a scale in which we have a bunch of reactions. They are all written as alpha reductions. So all you have is the reduction reaction that of course could not happen in isolation, right? But this has been measured respect to the oxidation of hydrogen, basically. So they are all written as a species acquiring electrons, so these are all reduction. The higher is the value, so the higher for all is fluorine. The higher is the tendency for that species to attract electrons and be reduced. So that means that fluorine is the strongest of all, and therefore is very effective in stealing electrons from other species. That makes it a very strong oxidizing agent. On this hand, we have lithium that has a very large negative value. This means that it has no tendency to attract the electrons at all. If I would flip the reaction, right, if I would write lithium arrow lithium plus 1 electrons, that would be the oxidation of lithium. That would have the same value but with a positive sign. So for lithium there is a very, very strong tendency to get oxidized, to lose electrons. So lithium is a very strong reducing agent. So probably in a parallel universe, they have a standard oxidation potential table where everything is flipped around. But as a convention, we decided to use as reference the reduction reactions. So let's have a closer look to this table and figure out some important reference points. So for example, let's figure out where hydrogen is, and this is the 0. So for every reaction that's below, you have negative values. For every reaction that's above hydrogen, you have positive values. So how do you use the relative position to predict the reaction? So let's take, for example, copper. Now you need to be careful when you look for reaction in this table to pick the right one. You see you have a copper immediately above hydrogen, but that is gaining only 1 electron. The reaction that I want really is this one, where copper is getting 2 electrons. The potential is 0.34. That is larger than the potential of hydrogen. So because copper has a higher value, that tells me that copper is the oxidizer, is getting reduced. So the larger is the species that has the largest number for the reduction potential is the one that's getting reduced. So it's the one that's going to be the cathode. The species that has the lowest value is the one that is less likely to be reduced, therefore is the most likely to be oxidized, therefore is going to be the anode. So they tell me that if I put together copper and hydrogen, copper is going to be the cathode, hydrogen is going to be the anode. Hydrogen is going to be oxidized, so H2 is going to give off electrons to copper, and copper is becoming copper metal. If instead I go and take, let's say, zinc, that is here, zinc is below hydrogen and is below copper. So if I pair up zinc and copper, between the two, the cathode is going to be copper because it has the highest value and is getting reduced. The zinc who's going to have the lower value, is going to be oxidized and is going to be the anode. So if I want to produce energy from a reaction between copper and zinc, I need to take copper ion and metallic zinc so that the zinc can be oxidized and copper can be reduced, because that's how spontaneously it would happen. If I take metallic copper and zinc ions, hoping that the electrons would go from copper to zinc, that's not going to happen, because between the two, copper is the one that attracts the electrons more strictly. However, if I pair up the copper with the silver, now let's go and find the silver, here it is, then what happens is that this time silver is the one that has the highest value, 0.80, as opposed to copper that is 0.34. So now silver is, if I pair up silver and copper, silver is going to be the cathode, it's going to be reduced, and copper is going to be oxidized, and not the other way around. So that ranking of metals may remind you of the activity series of the elements. There are some differences, but in both you have the hydrogen as a reference point. The activity series is an empirical series, means it's built up through experiments, while the electrochemical series has numbers and has theoretical calculation behind it. The other difference is that in the activity series of the element you have only metals, while in the standard reduction potential table you have much more variety of reactions. But again, the relative position is telling you which reaction is going to happen. So copper is below hydrogen, zinc is above hydrogen, copper is below zinc, so copper is getting reduced and zinc is getting oxidized. But it's kind of flipped, typically, the order, like what's up and what's down, so that's a bit. So let's go back to our example of the zinc and copper voltaic cells. So we can either measure the potential of the cells by introducing a voltmeter in the circuit, or we can do the math and calculate the theoretical value by taking the values from the table of the standard reduction potential and using this formula. So the standard potential of the cell is going to be the standard potential of reduction of the species that constitute the cathode, minus the standard potential of the species that is at the anode. And the minus makes sense because at the anode you have the oxidation, so you have the opposite reaction respect to the one that's listed in the table. So for example, for copper, we could go to the table, we will find that the standard reduction potential of copper is 0.34, while the standard reduction potential for zinc is minus 0.76. So we can calculate that cell potential by going 0.34 minus 0.76. So that gave you a positive of 1.1. That tells you that this reaction designed this way is spontaneous, and you would know that even without having to actually perform the reaction and measure it. This is another example with copper and silver. So this time the copper is going to be the cathode because the silver has a higher standard potential that is 0.8 volt. So silver is going to be the cathode, copper is going to be the anode, and the difference is going to be 0.46. And you apply the same formula. Now the note that I choose this example because there is a coefficient of 2 in front of silver and a coefficient of 1 in front of copper, but these coefficients do not appear in any shape or form in the formula. So you don't have to multiply or you don't have to elevate to any power. These values are already standardized and they don't require to be corrected for the coefficient. A way to represent galvanic or voltaic cells in a short and concise way is the cell diagram. That's a sort of a shorthand notation. So let's take, for example, the reaction between copper and silver. The cell diagram consists in a string where you start by writing the anode, the species that are in the anode, and then you write the species that are at the cathode. And the two are separated by this double vertical line that sort of represents the salt bridge. So here you have the anode, and here you have the cathode. And you're going to write the reactant first, and then the product for the anode, and then reactant and products for the anode. So let me get the laser point. So reactant and products for the anode, and reactants and products for the cathode. And the reactant and the products are separated with just one vertical line. So if you have something that's dissolved in water, like in this case, the product of the reaction is copper ions, and one of the reagent is silver ions, you also need to write the concentration. So, and that's all. Now, typically when I ask a question about the cell diagram, students get confused and think they have to do the drawing. But this is not the diagram, this is the diagram. However, again, this is going to be at this point all multiple choice, so it's no big deal. But sometimes you may have the information for the cell given in the form of the diagram. So instead of having the actual reaction spelled out, you may have the diagram. So you may be you need to be able to reconstruct the reaction. So this, when given this, okay, so you know that this first half is the anode, so is the species that's getting oxidized. Copper solid is written first, so is the product, so you write copper on this on the right, and then you write copper ions on the left, and then silver on the right and silver ions on the left. A cell diagram is a sort of a concise and quick way to write all the information that you need about voltaic cells. So a cell diagram is composed of two halves. You have the anode, and then you have on the left you have the cathode. So you can see the cell diagrams here. So the cell diagram consists in these strings of characters. So the anode is separated by the cathode by this double vertical line that represent the salt bridge. On the left of the salt bridge you get the information about the anode. So you have, first of all, you have the reactant, and separated by just one vertical line you have the products, and in this case is copper solid getting oxidized to copper ions. That makes sense because this is the anode, so this is where the oxidation happens. In the cathode you have the reduction, so the reactant is silver ions getting reduced to metallic silver. If you have aqueous solution, you would also need to indicate the molar concentration of the species. So what if the conditions are not standards, right? So the cell potential in standard condition can be calculated as the difference between the standard reduction potential at the cathode, so as can be read in those tables that we were talking about, minus the standard reduction potential of the anode. For the condition to be standards, we need to have temperature of 25 Celsius. That's pretty much happens most of the time because the reaction, the cell may be built up in a lab situation where the temperature is pretty much that. The concentration needs to be 1 molar. That's more likely not to be met, that condition, because normally concentration tends to be smaller than 1 molar. If you have gas species, the pressure needs to be 1 atmosphere. It's unlikely that you, excuse me, that you really have to deal a lot with situation where one of the reactants or the products is a gas, and you have to do math with it. So if we have if we are in a non-standard condition, we use the Nernst equation, and that consists of making a correction to this standard cell potential. So you still have the standard cell potential here. So this one in green is the potential in non-standard condition. So it's equal to the potential in standard condition in yellow. And then there is a correction factor. So you need to subtract this whole chunk of the equation. So 2.303 is the conversion factor between decimal logarithm and natural logarithm. In fact, you may notice that here you have the logarithm, the decimal logarithm. That's the logarithm of Q. Q is the reaction quotient. So you need to take the molar concentration of the products divided the molar concentration of the reactant. So this factor is important when you have concentrations that do not match standard. They are not 1. If the concentration would be 1 molar, for both reactant and products, regardless of the coefficient in front of those pieces in the balance equation. Remember that when you calculate Q, the concentration needs to be elevated to a power that corresponds to the coefficient. So if the coefficients are all 1, fine, but even if they're not 1, if the concentration are 1 molar, 1 elevated to whatever power is still 1. So regardless of the coefficient in the balance equation, if the concentration are 1 molar, and that would be standard condition, Q becomes equal to 1. The logarithm of 1 is 0. This whole factor surrounded in blue becomes 0, and the standard potential is equal to the potential in non-standard condition. So T is the temperature in Kelvin, R is the Gauss constant, that needs to be the one with the joules unit. F is the Faraday constant. The Faraday constant tells you how many coulombs correspond to 1 mole of electrons. So it takes 96,500 coulomb to make 1 mole of electrons. And N is the number of electrons exchanged in the reaction once you have balanced the equation. So at 25 Celsius, this can be simplified because T would be 25. So everything, let's see, everything surrounded by the green line would be a constant except N. That depends from one reaction to another. So it can all be summarized in these numbers. So this makes the Nernst equation easier to handle, because as I said, 90% of the time the conditions are not standard because of Q, and everything else is standard. So really the only thing you need to keep in mind is Q. So let's see an example of non-standard condition. We have the reaction between aluminum and manganese, and once it's balanced, there is a 2-to-3 coefficient ratio. So we are asked to calculate the we are asked to calculate the cell potential at 25 Celsius, and that would be standard for a concentration of aluminum that's 2 molar and a concentration of manganese that is 1 molar. So it's the concentration that are not standard. So we can use the simplified version of the Nernst equation, and because the only correction is due to a different Q. So first of all, we calculate the standard cell potential by subtracting the standard reduction potential of the cathode. So we go on the table, we figure out which one is the cathode, and we take that value minus the values at the anode. Now, which one is the cathode? The cathode is going to be the one that's getting reduced. Now, aluminum is going from 0 of oscillation number, so it's neutral, to +3, so it's getting oxidized. So therefore, the species that's reduced is manganese. So it's going to be the standard reduction potential of manganese minus the standard reaction potential of aluminum. Again, you don't have to worry to calculate a cell in standard condition. You do not have to worry about the coefficient. The coefficient are not changing those numbers from the table. So you figure out that the standard cell potential is plus 0.48 volt. Then you need to calculate Q. Q is going to be the concentration of the aluminum ion, because aluminum is the product, divided the concentration of the manganese ion, because manganese is the reactant. Manganese concentration needs to be elevated to the third power. Aluminum needs to be elevated to the second power. Disclaimer, I believe this is not, if not identical, is very similar to the post-lab question you have in your lab manual. But even if the numbers are not the same, the procedure is very much alike. So once you've calculated Q, you just plug the numbers. Now, the number of electrons is 6, right? Because each aluminum is giving off 3 electrons because it's becoming 3 plus. But I have 2 in front of aluminum, so 2 times 3 is 6. And 3 manganese ion times 2 positive charge, it means that 3 manganese ions need to acquire a total of 6 electrons to become neutral. So this is the N that you need to plug into the equation. So you see that the value changes not a lot, right? So normally these modifications due to the change in concentration are not dramatic in terms of changing the voltage potential. That's a pretty typical situation. The cell represented here is a particular type of cells that's called concentration cells. It's kind of unusual because you have the same species on both sides. Both electrodes are made of solid copper, and in both alpha cells you have a solution of copper ions. The only difference is how concentrated is the copper ions in the two solutions. So you can see here that on the right you have the more concentrated solution, 1 molar, and on the left you have the more diluted concentration, 0.1 molar. So this side of the diagram is the starting point. This side of the diagram is where the cell would stop working. So this is a spontaneous reaction. So this could be used as a battery and would generate a difference of potential that you can see highlighted here. It's 0.0296 volt. Eventually the battery gets exhausted. And you have a potential of 0, at which point you don't have any electrical energy generated. You get 0 when the concentration on the two sides becomes the same. So you would have the same shade of blue, basically, right? So what's going on here is that you have on the right side, you have the diluted concentration. This is the anode. So on this side, you have an oxidation of copper. This is going to use up this electron. So this electron is going to get thinner and thinner. The copper ions concentration in the solution is increasing, so this solution is getting more and more blue. The electrons are flowing into the circuit. They're going to the other side, where they're going to react with the copper ions in the solution, reducing them into metallic copper. So on this side you have the reduction, you have the cathode. So because the copper ions are used up, this side is getting less and less blue. So by the time you're done, you are going to have the same shade of blue. So it's a bit like mixing two solutions. You see, like one has a lot of copper ions and one doesn't. And once you mix them, they would reach a steady state where the color is somehow intermediate between the two initial colors. So here is the same tendency. Where there is less copper, the spontaneous trend is to increase it. Where there is more copper ions, the spontaneous trend is to decrease it. By the end of the reaction, you would have used up a bunch of the material in the anode, so the anode is going to be almost like corroded, so like thinner, so the mass is going down, while on the cathode side you're going to have a deposit of copper, so the mass is going up. And you can see that the concentration of copper at equilibrium is the average between the two initial copper. So it's like 1 plus 0.1 is 1.1 divided 2 is -55. So the obviously, because of the weird concentration, this is not standard condition, right? But because the temperature is 25, we can use the sort of a short version of the Nernst equation, right? So first of all, we calculate the standard potential, but because it's the same reaction, copper and on both sides is going to be 0.34 minus 0.040. So there is no driving force coming from the species. Where the driving force is coming is the difference in the concentration. So on top you have the diluted, at the bottom you have the concentrated. So that means that the logarithm so here this ratio is going to be 0.1, 10 to the minus 1. The decimal logarithm of 10 to the minus 1 is going to be -1. Then you multiply by this, but there is a minus, so it becomes plus. So the potential is going up, it's becoming positive, not a huge value, but it's a positive value. This tells you that the reaction is spontaneous. But as you see, it's not dramatically different from is not just a lot, that's what I'm saying. But it's enough to drive the reaction. Now, what's interesting is that's how our cells, our nervous system and muscular system works. So our body relies on electrical signal. Our wires are the nerves, and our batteries it's a concentration cells due to the fact that sodium and potassium have different concentration between the two sides of cell membranes. Sodium is highly concentrated outside cells, and potassium is highly concentrated inside cells. So those two combined create a difference of potential across cell membranes that sustain all the electrical signals that are responsible for our heartbeat, the functioning of our nervous system, and the contraction of our muscles. So voltaic cells can be classified into three main groups. Primary cells are those in which the reaction is unidirectional. It goes only one way, is irreversible. So that would be a battery that when it's exhausted, you need to throw it away. You cannot recharge it. Secondary cells instead are rechargeable batteries. So once the battery is exhausted, you can connect it to an external power source and you can recharge it by forcing the reaction to go the opposite way. That would be an example of that would be the battery in your car. Tertiary battery are fuel cells. Those can work in a continuous way. You don't have to stop it, recharge it, and then so you don't have to go back and forth between running it as a voltaic cell and then as an electrolytical cell and then as a voltaic cell. They can be recharged continuously. Just want to remind you some other terminology. The salt bridge, there can also be a porous sept. It's just a different design, but it's the same functional role. It connects the two alpha cells so that the circuit is closed. It has to be filled with a solution that is thick enough to avoid mixing the content of the cells, but it allows moving of spectator ions to keep the two solution in the two alpha cells neutral. And electrodes can be, let's say, classified as active or inert. Active electrodes are part of the reaction, so they would show up as a reactant or as a product. They would be oxidized or reduced, so they would change their mass. Inert electrodes are electrons that do not participate in the solution, so they are not oxidized, they are not reduced, their mass is not going to change. Typical example of inert electrode is platinum or graphite. So what are these fuel cells? In fuel cells, the reagents are continuously added and the products are continuously removed. So you don't need to stop the functioning to recharge it. It can go on and on for a very long amount of time. The most common used type is the one that uses the direct combination of hydrogen and oxygen to make water. This is a strongly exothermic and spontaneous reaction. You have at the cathode, you have the reduction of oxygen, because in water the oxidation state of oxygen is 2-, while in the elementary oxygen is 0. At the anode, you have the oxidation of hydrogen into hydrogen plus 1. So hydrogen and oxygen are relatively cheap and abundant material. Water has no harm on the environment, so you can understand that this reaction has a lot of appeal in terms of being environmental friendly. This is a reaction that is used to propel rockets for space exploration, because you can just store the hydrogen and the oxygen in tanks in the rocket. The use of this reaction in an electrochemical setting, as opposed of burning hydrogen and oxygen, that would give off a lot of heat, right? But then you remember there is the second principle of thermodynamics that kind of limits the amount of energy that you can extract by thermochemical reaction. So by using an electrochemical approach, you kind of avoid that bottleneck, and you can actually make the reaction more efficient. Let's see an example of how to do the math, and also how to write a diagram, a cell diagram. So we are asked to write the reaction between magnesium and copper. We have the concentration 0.1 molar for both ions. However, we are not given the reaction, so it's, how can you tell, right, which one is the cathode, which one is the anode? Because you don't know which one is oxidized, which one is reduced. But you know that is a voltaic cells. If it's a voltaic cells, it means it's spontaneous. If it's spontaneous, the standard reduction potential is going to be positive. So the only way is that the cathode is going to be the one with the highest standard reduction potential, and the anode is going to be the one with the lowest. So magnesium needs to be the anode, and copper needs to be the cathode. This way, when you go to calculate the standard potential for the cell, is going to be equal to the potential at the cathode. So if copper is the cathode, you're going to have plus 0.34 volt minus the potential for the anode. If the anode is magnesium, is going to be minus 2.37. So this is the only way, this combination is the only way where you can come up with a potential that's positive. That's going to be about 271. I'm just doing the math at the top of my head. Because if you switch them, it is going to be minus 2.71. So in order for that to be positive, it has to be that the copper is the cathode and magnesium is the anode. So once you have figured that much, you can write the two half reactions, right? So magnesium is oxidized to magnesium plus 2. Copper is reduced to copper, metallic copper. Because both are exchanging 2 electrons, they're going to react in a 1-to-1 ratio. So we can write the cell diagram in which we put the anode first at the magnesium side. Magnesium is going to be, solid magnesium is going to be the reactant, and magnesium ions are going to be the products. And we need to specify the concentration 0.1. So it's important that you remember to divide the two half cells with the salt bridge, so the 2 vertical lines, and product and reactants are separated by 1 vertical line. Now, if you're going to calculate Q, right, so this is non-standard condition, There is no mention of the temperature. Let's say the temperature is 25, so that's not the issue. But the concentrations are not 0,1 molar, so we are not in constant standard condition. So what is Q? Q is going to be the concentration of the magnesium, that's going to be 0,1 molar, because magnesium is the product, divided the concentration of the copper, that's going to be also 0,1 molar. So Q is going to be equal to 1. The logarithm of Q is going to be 0. So even if the concentrations are not standard, and we were supposed to use the Nernst equation, because of logarithm of Q being 0, we are going to end up having the potential of the cell identical to the standard potential. That's what's going to happen in the lab. The concentration is 0,1 molar for all the cells you're going to test. And even if you're not in standard condition, you're just using this equation up here instead of the Nernst equation. That's because the concentrations are the same above and below, so Q would become 1, the logarithm of Q becomes 0, so there's really no difference. The only one for which you have a difference, potentially, is silver, because silver exchanges only one electron, and so the reaction between silver, let's say, for example, and copper, is a 2-to-1 ratio, so you would have 1,0,1, let's say that silver is at the bottom, you would have 0,1 on top, and you would have 0,1 to the second power at the bottom. So this Q doesn't become equal to 1 anymore. But you can do the math and you would see that the difference is really, really minimal. And I put a note about this at the end of the lab procedure. So if you are curious about that, just read that at the very end of the lab procedure.